This is the problem on the jet engine, and actually you'll find it towards the beginning of this problem section, and I guess in hindsight I figured, oh, I might as well do the problem, and that's why you find it in the back of my recordings, but I guess that doesn't matter. Okay, the problem reads, the drawing shows a jet engine suspended beneath the wing of an airplane. The weight of the engine is 10,200 newtons and acts as shown in the drawing. In flight, the engine produces a thrust T of 62,300 newtons that is parallel to the ground. The rotational axis in the drawing is perpendicular to the plane of the paper. With respect to this axis, find the magnitude of the torque due to A, the weight, and the thrust. Notice they don't ask about the direction of that, but actually you will see I'm able to write that down. So let's see what is given here. They tell us what the thrust and what the weight are, so they're given. They tell us what the lever arms are. And by the way, we have to point out that as the thrust is pointing to the left here, this one here is not the lever arm. This one is the lever arm. So just the vertical component of this original lever arm is the one that applies to the torque, because that one is perpendicular to that force, as it's supposed to be for calculating torques. And for the weight, it's the same thing. This one here is not the lever arm for the weight. It's this portion, this component of that lever arm, which means, yeah, we have to look at this one here in this triangle for the lever arm for the weight, again, because it's perpendicular. And that of course means that or they're asking for what the torque is, and that of course means that, well, with this one, with these two here given, and the torque is what's being asked for, then this one here is what we have to use. Straightforward. The torque equals a force times the lever arm, as long as the two are perpendicular, and I'm going to put that in parentheses and write this down here, as long as it's perpendicular. And now the problem can be done in two ways, and that is that, for example, for the weight, I have to use this component here, and if you look at that, if you look at the drawing here with this one being opposite, I would use the sine of 32 degrees in order to come up with that lever arm, so sine of 32 degrees times the 2.50 meters, and then I do something similar for the thrust, that this one is actually the lever arm, and I calculate the cosine of 32 degrees times 2.50 meters, and that's the way the book is doing it. And then there's a second way of doing it, and that's the way I argued in a previous problem, that technically we're looking at the angle between the force and the original lever arm, and that then will give us the torque. And that's the way I'm going to do it here. Either way you do it, the outcome will be the same. I'm going to start out with the torque, which with the thrust, which is actually part B, and I calculate the torque due to the thrust as the thrust times the length of the original lever arm times the sine of that angle between the two, between the force and the lever arm. And notice if this one is 32 degrees, then this one here must be 58 degrees. So that's the way I write this down. So notice that this symbol here, the two have to be perpendicular to each other, then introduces the sine of whatever the angle is between the two. The L here is still that 2.50 meters, and then I say equal, and you can see what you come up with. Notice a moment ago I said in mid-air that the lever arm for the thrust, which is this one here, this is the lever arm for the thrust, is the cosine of 32 degrees. So if you calculate the sine of 58 degrees or the cosine of 32 degrees, the outcome is exactly the same. So either way you do it, you come out with the right result. I'm just doing it this way here because it's actually the proper way of doing it. The torque is the force times that original lever arm times the sine of the angle between the two. You're going to come up with some number, and it will be in Newton meters, and you're going to write these as Newton meters for the torque. You also come up with a direction, actually, because the thrust is pointing to the left and the lever arm is pointing down, so both of these are negative. And then they don't ask us for the direction, and I'm glad that they don't. I do this a little bit later here because there's a little bit of a trick to it for the direction of this torque that they don't explain in the book. I guess that's a topic for a different day, but I'll do it here a little bit later. Okay, anyway, the torque for the weight comes out as being the weight times, again, the original lever arm times the sine of the angle between the lever arm and the weight. And here I would have to extend this line here to write down the angle, and this angle in between here is of course the same as this one here. This was supposed to go straight down. Let me see if I can do this. There, it looks a little better. So again, this is also 32 degrees. And again, in mid-air, you heard me say earlier that we're also looking for the lever arm here, the short one here, which is opposite, so sine of 32 degrees. Again, either way you do it, the way you do it with the book, which looks primarily at looking at the correct lever arm, or if you do it with the way I explain it, the angle between the two, you come up with the correct result, and the angle between the weight and that lever arm is 32 degrees. And again, of course, that's going to be in Newton meters. And again, they don't ask for the direction. And basically, I'm actually done with this problem here because that's what they asked for.